Hello everyone, my name is Sagarika Srinivasan and this is my video lab report for Lab 3, Black Hole and Orbits. This lab had two primary objectives. First, to determine the mass of an unknown black hole that a star is orbiting, and second, to find a safe initial velocity for a starship to orbit both a planet and its moon without crashing. For part 1, we have finding the black hole mass. We analyze the motion of a star with mass of 2.0 times 10 to the 30 kilograms orbiting an unknown black hole location starting at the origin. The time step between the data points was set to 1 Earth day, or 86,400 seconds. The core of the analysis was using Newton's second law in the form of the momentum principle. We calculated the net force on the star using the rate of change of its momentum, delta P over delta T. We assumed that this net force was entirely the gravitational force exerted by the black hole. Therefore, we set F net to be equal to the force of gravity and solve for the mass over all data points. We reported a single answer by calculating the average of all of the resulting masses, which is 1.49 times 10 to the 34 kilograms. Next, we had part 2. In part 2, we simulated a system with a planet at the origin, an orbiting moon, and the spaceship starting on the moon. The goal was to find a safe initial velocity for the starship that would allow its trajectory to be influenced by both the planet and the moon. The computational model calculated all the necessary gravitational forces on the moon and the spaceship. We used Newton's second law to update the momentum and position of both bodies. While the goal was a figure 8 orbit, which proved challenging, I found a specific initial velocity that resulted in a successful non-crashing trajectory influenced by both bodies, which met the lab's requirements. In terms of the major takeaways of our project, a key part of part 1 was decomposing the rate of change of momentum into its components. We have the parallel component, which was the component that was parallel to the star's momentum or velocity and was responsible for changing the speed or magnitude of the star's momentum. We have the perpendicular component, which was responsible for the direction of the star's momentum, causing orbital curvature. Next, we had some conceptual questions. In terms of what does it mean, we have the net force of F net and the rate of change of momentum are mathematically equivalent, but they represent different things you can observe and measure. Net force is the cause of the change. It relates to the physical interactions such as the gravitational force exerted by the black hole. And the rate of change of momentum is the effect. It's calculated from the observed motion data showing how the velocity of the star is changing. Then we had the what if of the entire system. If I wanted to predict the motion of the entire imaginary system, the black hole, the star, the planet, the moon, and the spaceship, the model would need to include the gravitational interaction between every single pair of the 5 objects. We had the dominant interactions, which were the interactions involving the most massive objects, primarily the gravitational pull between the black hole and the star, which would be the biggest contributor to the system. But we would also have other contributions, such as the forces involving the relatively small spaceship would contribute, but they would be least dominant compared to the other forces. This was my GlowScript output for part 1, where we had at the center the black hole and the star orbiting the black hole. And this was my GlowScript output for part 2, where we had the sun in the center, we had the moon orbiting around the sun, and we also had the spaceship. This was the coding section. I added 2 snippets of code. The top part was from part 2, where we had to calculate the net force on the moon, and we did a similar thing for the spaceship. And the bottom snippet is from part 1, and it includes a lot of the vector components that I needed to calculate in order to get the sun properly orbiting around the black hole. Thank you so much for listening. Yeah.